बेटा तैयार हो जा। देखो ना फीवर है।
Welcome students, welcome to Unacademy, India's largest learning platform. Okay, let me introduce first myself. Okay, 15. I am Sunil Manjani. I got 15 plus years of teaching experience. Okay, I mentored thousands of students for GATE ESE semester exams, cracked PhD exams like GATE, HAL, MAHADISCOM, MAHAJINCO, etc. Okay. So let us see how to install Unacademy and how to use it, the application. Go to Google Play Store or App Store, type in Unacademy, you will get this Unacademy Learning App with this symbol. Install this, okay. After some permissions and registration, you will go to step 3 where you will go to manage goals, select GATE and ESE in the manage goals, then select plus, okay. After that, press get subscription button, okay. You will be prompted to select the package, okay. Plus subscription 12-month package is 27,225 and 24-month package costs you 39,600. Iconic subscription package 12 months costs you 45,225 and 24-month package cost you 66,600. Okay, so SSM10 is your is my inputting for further 10% discount. Okay, so what is plus subscription? India's best educator teaches you interactive live classes, structured courses and PDFs, live tests and quizzes. Okay, iconic application is India's best educator teaches you interactive live classes, structured courses and PDF, live test and quizzes. Okay, this is all plus features. Apart from this, you will get a personal coach, personalized test analysis, study planner, proprietary study material. Okay, so let us move on to our MATLAB fundamental course. Okay, so in this course, in today's lecture, we are going to discuss pole zero plot. Pole zero plot. What is a pole zero plot? We discuss numerous example with this. Okay, how to plot pole zero. Okay, what are the okay, so what is pole zero plot? What are poles and zeros first of all? Okay, so let us say we have got polynomial PS in terms of S term, in terms of S terms, NS terms and DS terms. This is numerator polynomial and this is denominator polynomial. Okay, numerator polynomial and denominator polynomial. Let us see how to use this both numerator polynomial and denominator polynomial. Let us see. This is s raised to n, a0 s raised to n, a1 s raised to n minus 1 plus a2 s raised to n minus 2 plus dash 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 plus an. divided by b0 s raised to m plus b1 s raised to m minus 1 plus b2 s raised to m minus 2 plus bm. Okay, so where ns is the numerator polynomial. ds is equal to denominator polynomial. Okay, so from that a naught, a1 up to an are numerator coefficients. Okay, dear students, so here b naught, b1, bm are denominator coefficients. Okay, so let us check what are zeros. First of all, I am saying pole zero plot, so let us check poles first. What are poles? These are the roots of denominator polynomial such that denominator polynomial becomes 0 and transfer function es tends to infinity. Okay, so let us say, okay, so denominator polynomial can be written as s minus b0 raised to n, s minus b1 raised to n minus 1, s minus b2 n minus 2. Or you can also write down denominator polynomial as s minus b0, s minus b1, s minus b2 and so on. S minus Bm rather. Okay, so this is denominator polynomial. Okay, so if this tends to 0, I will say that S minus B0. So ds tends to 0 implies S equal to B0, S equal to B1, S equal to B2, dash 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 S equal to Bm. So I will say B0, B1, B2, dash 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 Bm are roots of denominator polynomial. Okay, are roots of denominator polynomial. Let us check now if these are the roots. Okay, so total polynomial ps is ns by ds. So if I put this value of s to denominator term will become 0, ps will become infinity. Okay, so these are called as poles. So what are called as poles? These are called as poles of a transfer function. Transfer function. Let us check next. Okay, zeros of transfer function. What are zeros? When numerator polynomial is equal to 0, total polynomial becomes tends to 0. So the roots of numerator such that numerator polynomial becomes 0 are called as zeros of transfer function. So what are the roots? S minus a0 numerator polynomial equal to S minus a. S minus a1, S minus a2, S minus an equal to 0. Okay, equal to 0. So S is equal to a0, a1, a2, a3 and an. So these are called as zeros of transfer function. Zeros of transfer function. Okay, so let us say that when I am plotting pole 0 location, rather I will say location I will say I will plot this pole 0 location like this. Okay, pole 0 location on which graph? So graph used for pole 0 location is called as S plane, where x axis plus y minus y. Okay, so x axis, this is called as positive x axis is called as plus sigma, negative axis is called as minus sigma. Okay, positive y axis called as j omega, negative is minus j omega. Okay, now consider this, why this is the case. Consider this. Okay, whenever I have got a reference in positive x direction and I want to rotate this reference by 90 degree in anti-clockwise or counter-clockwise direction. I need to multiply this by j term, by j term only. Okay, so j is nothing but one angle 90 degree. So this will be j term. So similarly here you can see that here, okay, this is real axis, all this, and this is imaginary axis, imaginary, okay, imaginary axis, because poles and zeros poles and zeros are nothing but poles and zeros are nothing but roots, isn't it? So roots of polynomial can be real, distinct, okay, and simple. Roots can be real, repeated, repeated. Roots can be complex, and when they are complex, they are always conjugate. They are always conjugate. Okay, so I will say that simple distinct roots. Okay, what are simple distinct roots? Suppose there is s equal to a1, s equal to a2, s equal to a3. These are the example. A1 is not equal to A2 is not equal to A3. Okay. Simple repeated roots. These are nothing but S equal to A, S equal to A, S equal to A. So this will occur when S minus A whole cube is equal to 0. Is equal to 0. So these are repeated root. Next is complex conjugate root. Complex conjugate root. So S is equal to plus minus sigma plus minus j omega plus minus j omega, which implies that S can be sigma plus j omega and sigma minus j omega. Okay, or S can be equal to minus sigma plus j omega and minus sigma minus j omega. So these are conjugate pairs. Conjugate pairs. Okay. So in this way roots are referred. Okay. So how to draw the pole zero plot? When I am saying S equal to A1, so it is real roots. A1 is greater than 0. A2 is also greater than 0. A3 is also greater than 0. Okay. When I am saying it is S equal to A, S equal to A, S equal to A. Let us say S equal to A is here. This is A. This is another A. And this is third A. So these are multiple roots. Multiple roots. This is pole zero plot. Pole zero plot. Okay. Now complex. Now complex plot. Okay, this is plus j omega minus sigma minus j omega. So if there are two types of roots, okay, two types of complex root. First is where imaginary part, real part is positive. The real part is positive. Suppose this is j omega 1. This is equal to minus j omega 1. This is equal to, suppose, sigma 1. Sigma 1. Real part is sigma 1. So there are two roots. First of all, sigma 1 plus j omega 1. Okay. Second root is sigma 1 minus j omega 1. Okay. Second pair is when the real part is negative. When the real part is negative. So let us say that this is j omega 2. This is j omega 2 minus, okay, this was plus, this is sigma 2 minus sigma 2. So this will be your root. Okay, this will be your root minus sigma 2 plus j omega 2, and this will be your root minus sigma 2 minus j omega 2. So these four combinations or two combinations are rather which roots? Complex conjugate roots. Complex conjugate roots. So in this way you can plot the pole zero mapping. When I am saying you are plotting pole zero map, pole zero plot, it is also called as pole zero map. So whenever there is a stability point of view, whenever there is a stability point of view, okay, the pole zero map or pole zero plot, okay, this is S plane, has two parts bifurcated along the okay, okay. So part to the right of y-axis is called as y or imaginary axis. This is imaginary axis. Part to the right is called as right half of S plane. Part to the left is called as left side, left half of S plane. And whenever you are saying that, zeros, these are denoted by circle. These are denoted by circle. Okay. whenever I am saying that poles are denoted by cross. Poles are denoted by cross. In this way you can find out, or rather construct a pole zero plot. You can construct a pole zero plot. Okay. So in MATLAB, whenever you want to draw pole zero plot, it specifies that it is a pole zero. You want to do pole zero mapping. Pole zero mapping. Okay. So what are the commands? And what is the description? First of all, command is pz map system. Okay, so it plots pole zero map of continuous or discrete time LTI model. Continuous or discrete time LTI model. Okay. Next one is PZ map sys1 comma sys2 plots pole zero map of several LTI models in single plot. Next one is PZ map numerator comma denominator plots pole zero plot or pole zero map from polynomial coefficients. Okay. Next is P comma Z is equal to PZ map sys returns O system poles and zeros in column vectors P and Z without plot. Without plot. Okay. So there is always a need to from where pole zero plot we can obtain pole zero plot from transfer function. Transfer function is numerator polynomial upon denominator polynomial. We can draw pole zero plot for this function, pole zero map. Okay, so there is a need to convert transfer function to pole zero or pole zero to transfer function, pole zero to transfer function. Let us see the command. Command and then description. What is command? Z comma P comma K transfer function to 0 pole ZP in bracket numerator comma denominator. This is the function. Okay, what is the description? Converts transfer function to pole 0. Numerator comma denominator is equal to 0 pole to transfer function. Okay, Z comma P comma K converts a 0 pole to transfer function. So these are the plots. Okay, so we'll see one example. So example 1, GS is equal to 5s square plus 8s plus 10 divided by s raised to 4 plus 4s square s cube plus 9s square plus 10s. So determine poles and zeros and map them in S plane. So how to write the program? Very simple. What is the first step? clear all the workspace variable. Next step is clear command window CLC. Then what we will do, we will write down numerator polynomial is equal to 5s square. See, 5s square plus 8s plus, this is not 10, this is 40. So this is 40. This is 40. So polynomial of coefficient of s square is 5, coefficient of s is 8, and other coefficient constant is 40. So this is numerator coefficient. Denominator coefficient is s raised to 4, coefficient is 1, s cube coefficient is 4, s square coefficient is 9, s coefficient is 10, constant coefficient is 0. Okay, 1, 4, 9, 10, 0. What you need to find out? Poles and zeros. So z comma p comma k is equal to transfer function is given, isn't it? We need 0 pole, transfer function to 0 pole n comma d. Okay, this will give you 0, this will give you pole, this will give you gain k, dc gain k, dc gain k. Okay, this will give you dc gain k. What is next? Okay, so we want pole 0 map. PZ map in bracket n comma d. Then you can write down grid on. Okay, let us see. Grid on. Okay, this is the one thing you can write down with pole 0 map. Pole 0 map. PZ map n comma d. Let us see, we perform this on hands on. Okay, so let us say clear all CLC. Okay, CLC. Okay, okay, n is equal to 5 space 8 space 40. D is equal to 1 space 4 space 9 space 10 space 0. This is numerator and denominator coefficients. Okay, then comes z comma p comma k is equal to transfer function. You can also write down one. Suppose I want system which gives me transfer function n comma d. Okay, then zpk is equals to transfer function to 0 pole in bracket, transfer function to 0 pole in bracket n comma d. Okay, n comma d. Then you can also write down pz map. Okay, sys. Okay, for the time we will see only this much of a program, this much of a program. Let us say we'll save this. Let us save this. Pz map. Okay, one. Save this. Okay, let us run this. Before running, let us go to change of directory. Change of directory. Okay, so again run this. This is a pole 0 plot. How many poles see here? Okay, these are zeros. How many zeros? Two zeros. Complex conjugate two zeros. How many poles? Four poles. One is at origin, other are not at origin. Okay. Two, sorry. One simple pole at origin, one simple pole at -2. Other two are complex conjugate poles. Okay, so let us see the figure. How many poles? How many zeros? Two. So two zeros. Circle. How many poles? One, two, three, four. Four poles. So this is a pole zero. Let us say we want grid lines. Grid on. Save this. Run this. Save this and run this. So this is a pole zero plot. Pole zero plot with grid. With grid. pole zero plot. Okay, in this way you can plot pole zero mapping. Pole zero mapping. Okay, fine. Okay, so let us take the example 2 of pole zero plot. Example 2 of pole zero plot. Okay, the poles zeros and gain of a transfer function are given below. Obtain the transfer function obtain the transfer function. Okay, poles are at s1 equal to -1, s2 equal to -2, zeros are at s1 equal to -1, s2 equal to -1 plus j 0.5, s3 equal to -1 minus j 0.5, s4 is equal to -2, gain k is equal to 10. Gain k is equal to 10. Okay, gain k equal to 10. Okay, let us write down the program. Okay, let us say zeros sorry, I will say poles. Where are poles? We will write a column vector s1 equal to -1, s2 equal to -2. So -1, -2, semicolon -2. So column vector -1, -2. It's a small p. Small z is equal to zeros. Okay. -1, semicolon -1 plus -1 plus 0.5 star j, semicolon -1 minus 0.5 star j, and -2. Gain k is 10. Let us find out n comma d is equal to 0 pole to transfer function z comma p comma k. Okay, z comma p comma k. Okay, so this is z comma p comma k. Okay, in this way you can find out the transfer function, numerator and denominator polynomial. Okay, then simply say print says n comma d. You will get transfer function. You will get transfer function. Okay, in this way you can define transfer function. Let us do this hands on. Poles equal to -1 semicolon -2, zeros equal to -1 semicolon -1 plus 0.5 star j star j semicolon -1 plus minus 0.5 star j semicolon -2. Okay, then I will say n comma d is equal to 0 pole to transfer function. Sorry, k we have to write down k equal to 10. So 0 pole to transfer function z comma p comma k. This is the completion. Grid on. Okay, so we don't need any plot. So this is zbk. Okay, you can write down print sys is equal to, or rather print sys n comma d. You will get transfer function. Okay, so here 0 pole to transfer function. So I will save it, then run this one. This is not equal b equal. Okay, so there is a little bit of correction. Little bit of correction. Okay, my mistake in the book. Sorry, in my notes. I have written down. These are actually zeros, and these are poles. These are poles. Okay, so zeros and poles are there. So just write down. Just change it. So if you see this, you will get the picture quite clear. 10s square plus 30s plus 20. Okay, so this is numerator comma upon denominator. Okay, so this is how to form transfer function from, sorry, yes, transfer function from zero pole diagram. Okay, so this is a little bit about pole zero plotting. We'll solve some example on pole zero plot. Okay, example. GS, oh sorry, FS is equal to s square plus 2s plus 3 upon s plus 2 whole cube. So this is here to evaluate, here to evaluate poles and zeros and map a plot, map pole zero. So what is the program? We'll see the program, then we'll write the program. Okay, CLC, rather clear all. CLC clear all. Plot the step response of unity feedback control system having forward path gain as follows. GS equal to 4 upon s square plus 2. S square plus 2s plus 3. Sorry, this is the program. Okay, so clear, this is a transfer function, clear all. CLC, write down is, we will write down numerator polynomial, coefficient 1 2 3. Okay, denominator is equal to convol 1 to 1 to 1 to. Okay, denominator polynomial, this is numerator polynomial. Okay, so numerator polynomial as well as denominator polynomial. Okay, so now we'll write down what is pole zero plot. How to find out pole zeros? Zeros pole gain is equal to transfer function to pole zero, zero pole in bracket n comma d, n comma d. Then I will say pz map is equal to pz map into this n comma d. Okay, also I will say print sys n comma d. Okay, so let us do it hands on this one. Let us do it hands on. Okay, clear all CLC. Numerator polynomial is how much? 1 2 3. Denominator is equal to convol, okay, 1 space 2 comma 1 space 2 comma 1 space 2. Okay, so ZPK transfer function to ZPND PZ map sys. Okay, you can do like this also. Okay, PZ map 2. Save this. Okay, run this one. Either do it like this or we will define another way to write down convol function. There may be a problem, sometimes the arguments they cannot take. So this is s plus 2 whole cube. This is equal to s plus 2 into s plus 2 whole square. S plus 2 s square plus 4s plus 4 So this is s cube plus 4s square plus 4s plus 2s square plus 8s plus 8. 8 is equal to s cube plus 4 and 2 6s square plus 12s plus 8. So D coefficients will be 1, 6, 12, 8. Just write this 1, 6, 12, 8. Okay. 1, 6, 12, 8. Okay. Save this one and then run. So three poles here and 1 0, 1 0 here, 1 0 here, 2 zeros. 3 poles and 2 zeros. Okay, in this way you can find out the answer. 3 poles and 1 and 2. These are 3 multiple poles at same location. Okay, so this way you can find out 5 number of roots. 5 number of roots. Okay, so if I say transfer function s square plus 2s plus 3 s cube plus 6s square plus 12s plus 8. So this is fine. Okay, so this is pole 0 plot. Let us solve one more example. Okay, what is the example? Example is fs is equal to 2 upon s plus 2 s square minus s by 2 plus 1.5. Okay, this is the example. So numerator coefficients will write down. Okay, naturally in the denominator s cube term is there, so s cube term in numerator is 0, s square term in numerator is 0, s term in numerator is 0, constant term in numerator is 2. Denominator is equal to, you can write down now convol. Okay, 1 comma 1 space 2 comma 1 minus 0.5 plus 1.5. In this way you can write down. So let us check with the hands on. Okay, what was n? N was 0, s cube 0, s square 0, s, and then 2 constant term. Okay, this equal to convol convolution of 1 space 2 comma 1 space minus 0.5 space 1.5. Okay, so in this way you can write down. First of all, let me delete this file of figure, save this one, then run this. So this system, you can see it is on right hand side, poles are on the right hand side, 2 poles. So this is unbalanced system. No zeros, as numerator does not have any s term, no zeros, constant term is there, so no zeros. Okay, so this is how to write down example. Another example, let us see one more example. Okay, one more example. Fs is equal to 1 upon s square s plus 2. So simply you can write down this as 1 upon s cube plus 2s square. What is numerator term? S cube term is there, s cube term 0, s square term 0, s term 0, constant 1. Denominator is equal to s cube 1, s square 2, s 0, constant 0. So 1 2 0 0 is your term. Okay, so let us make changes in the file. So this is 0 0 1. Okay, denominator we will say 1 space 2 space 0 space 0. Save this one. Okay, for the moment I will delete this file, figure file, and I will run the program. So see here how many poles. How many poles? See, denominator equal to 0. S cube plus 2s square is equal to 0. So let us say s square s plus 2 is equal to 0. S square is equal to 0. S plus 2 is equal to 0. S is equal to 0 comma 0. S is equal to minus 2. So poles are at origin. How many poles? 2 poles. At s equal to minus 2, how many poles? 1 pole. Okay, so 3 poles are there. So if you see the figure, you will get at origin 2 zeros, 2 poles. Okay, at origin 2 poles. Okay, at s equal to minus 2, 1 pole. Fine. Okay, let us solve one more example. Example, fs is equal to s square plus 8s plus 6 divided by s cube plus 2s square plus 3s plus 4. So numerator will be equal to 186, denominator is equal to 1 2 3 4, 1 2 3 4. Sorry, 1 8 6 1 2 3 4. Okay. Okay. So save this, close the file, figure file, then I will run this file. See this equation, above one is quadratic, so 2 poles, below one is having power 3, so it has 3 poles, 2 zeros, so total 5. 3 poles, 2 zeros. So you can see 0 is here. Okay, 1 0. Second 0 is here. 2 zeros. First pole, second pole, complex conjugate, and then simple pole. Okay. So this is how you get the poles. How you get the poles. Okay, so in this way you can plot the pole zero diagram. Pole zero diagram of a system. Okay, so this is how you plot pole zero diagram of a system. Okay, so this is how to plot pole zero diagram. Okay. Okay, let us check with some interesting theory before we conclude. Okay, in the control system, we see that okay, if we see that there is a pole on negative real axis, pole. Okay. So what is the effect of response? Effect of response on. So this is the response. Okay, step response. Let us say this is at A. So what is the response? This is the response. This is the response. Okay. Suppose say pole is at origin. Response is straight line. Pole is at origin. Okay. Pole is at origin. Suppose there is a double pole at origin. One pole, two poles. Okay. What is the response? Response is like this. Double pole at origin. Okay. Okay, I added some 3 slides so that we can discuss further. Okay. Suppose I have got complex conjugate poles on left half of the S-plane. Complex conjugate poles. Sorry, not here. On left half of the S-plane. What will be my response? Naturally, system is stable. Therefore, my response will be decaying sinusoid. Decaying sinusoid. Okay. Poles on right half of the S-plane, complex conjugate. System is unstable, then this is a rising sinusoid. Okay, let us say it is a marginally stable system. Complex conjugate pole on imaginary axis. So it is a constant sinusoid. Not decaying, not rising. It is a constant sinusoid. Okay, in this way you can find out in different okay. So one or two cases we will see. Okay, we will see one or two cases. Suppose case 1, poles on negative real axis. Let us say suppose this pole is on negative real axis -2. There is no zeros. No zeros. Only poles. No zeros means I will say n equal to 1. I'm writing in terms of MATLAB. D means how much? This is s minus 2 equal to 0. Denominator coefficient is s minus 2. So 1 minus 2. This is 0 base 1. Okay, like a denominator. So let us write 0 space 1. Okay, 1 space, not minus 2. Just a minute. So I think this must be plus 2. This must be plus 2. So plus 2. Okay, 1 and 2. So I will write down whole 0 map is system. Then I will say step sys. Let us see. Let us see. So this is the response. Let us see. I will make one changes. Case 2. Case 2. Case 2. Pole on positive real axis. Numerator is equal to 0, 1. Positive real axis means s is equal to 2. So s minus 2 equal to 0. So denominator is equal to 1 space minus 2. Fine. 1 space minus 2. So one space minus 2. Save it. Then run this one again. Let it computer up. See this response rising towards infinity. Rising towards infinity. Isn't it? Rising towards infinity. This I am plotting a transfer function. I am plotting a transfer function. Okay, so this is the case. Let us say case 3. This was case 2. Case 3. Pole at origin. Origin. Pole at origin. So whenever pole at origin means what I will say, n is equal to, that means transfer function will be like what? 1 by s. That means this is 0, 1. Denominator is equal to 1, 0. Alter tab. 0 1 1 0. Save this, run this one. See this figure. It is a straight line. It is a straight line. Now, what is the difference between this transfer function and the response I want to see? Response should be straight line, isn't it? So I want to see a response. I want to see a response. Okay. This is transfer function. I'm sorry. This is transfer function. That is CS by RS. One by S. 1 by S. Okay. So CS by RS. So what is CS? What is CS? 1 by S into RS. CS will be equal to 1 by S into 1 by S. Okay. So CS is equal to 1 by S square. Okay. For transfer function, if Laplace transform of t has a Laplace transform of 1 by S, inverse of 1 by S. So this will be t. So 1 by S square. Okay. 1 by S square. Okay. Okay. So in this way you can see the check the stability there for the system. Okay. So here we will complete this today's topic. Okay. So thank you very much. Thanks a lot. Okay. How to unlock free plan on Unacademy? Go to Unacademy Learning app. Go to daily interactive live classes. Manage your goals. Put in GATE and ESE. Put in GATE and ESE. So plus subscriptions like that one. You'll get many courses. You can watch it for free. Many videos, many PDF. Click on the particular video or the course of your interest. Okay. Then you will be prompted to write an invite code. Okay. So enter the invite code. Invite code of mine is SSM10. So enter that SSM10. Press unlock. Okay. Press unlock. After unlocking, you will get the access to free watching of course on Unacademy. Okay. So let us crack GATE and ESE. Okay. So like, subscribe, comment on our YouTube videos. Okay. Hit the bell icon for further notification. Okay. There is a Telegram group. Join the Telegram group for latest updates on our upcoming videos. Okay. So thank you very much. Thanks a lot. With this, I will sign off for today. Thank you very much.